Right. Hello, everyone. Thanks for coming to today's CDG Seminar. I'm standing in for Monica as she's at another workshop, although I think she might be online as well. So it's my pleasure to introduce Zoe Gillett, who's here from Australia. So she's been here for a couple of weeks and is going to be here for 2 weeks more. So if you're interested to talk to her, she's sitting in Rocky Dunlap's office, or you can get in touch with me and I can get in touch with Zoe if you can't find her email address. So Zoe got her PhD in 2021 from Monash University. She worked with Julie Arblaster, who we all know quite well, and Harry Hendon, and wrote an excellent thesis on Rossby wave propagation in the Southern Hemisphere and kind of the dynamics of how the subtropical jet affects propagation from the tropics into the extratropics, which I think is what we're going to hear about today. She's now a research associate at the University of New South Wales, working with Andrea Taschetto, and she's working on kind of ocean influences on drought now. So I'll hand it over to Zoe to talk about the teleconnections in the Southern Hemisphere.
Perfect. Thank you, Isla. All right, so thank you for the opportunity to speak and give a seminar here while I'm visiting at NCAR for these 4 weeks. So today I'm going to be talking about a couple of parts of my PhD thesis. And so this will be looking at understanding mechanisms of Rossby wave propagation from the Indian Ocean and Pacific Ocean into the Southern Hemisphere. So, sorry, that's very bright. But I'll motivate this work by sort of giving an overview of the typical tropical to extratropical teleconnections that we see in the Southern Hemisphere, and also contrast this with what we see in the Northern Hemisphere. And so in the Southern Hemisphere, these are largely associated with the Indian Ocean dipole and with ENSO. And so I've shown here 2 schematics that show the typical patterns that we see during the positive IOD and El Nino. So focusing first on the positive IOD, so this is when we have warmer sea surface temperatures in the western pole of the Indian Ocean and cooler sea surface temperatures in the east. And so during austral winter in June, July, August, this pattern of cooler sea surface temperatures in the eastern Indian Ocean, and so this suppressed convection that occurs, is associated with a poleward and eastward propagating wave train. And so this wave train during winter largely comes from the eastern pole of the Indian Ocean. And during the same season, associated with El Nino convection in the central equatorial Pacific Ocean, we see this poleward propagating wave train, the Pacific South American pattern. In spring, the ENSO and the IOD are more strongly correlated compared to winter. So the correlation is 0.72. And so what we see is actually some more sort of a combination of these wave trains. And this is because El Nino contributes to some forcing of the positive IOD pattern. And so what we see is this PSA pattern in the South Pacific Basin. And then also a wave train emanates from both the western and the eastern poles of the Indian Ocean during spring, when there's greater coherence between these 2 poles. And so we see that both poles of the Indian Ocean contribute to this high anomaly to the south of Australia, and both the Pacific Ocean and Indian Ocean wave trains contribute to this broad low across the South Pacific. So this connection between ENSO and the IOD in spring is quite important for understanding how ENSO influences Australian climate. Because Australia is upstream of the Pacific Ocean, it's not sort of immediately obvious how it influences Australian climate, and that's because part of this ENSO impact comes through the IOD. And so this is in contrast to the Northern Hemisphere, where during spring we start to see the establishment of the Pacific North American pattern, and North America is located downstream of this pattern. So the atmospheric circulation is important for these tropical to extratropical teleconnections. So I'll just give a brief sort of overview of the typical pattern, the sort of structure that we see during Southern Hemisphere winter and summer. So the subtropical jet has an important role, and so this sits at the edge of the Hadley cell in the upper troposphere, where it's largely confined. And so it's largely a thermally driven jet, compared to the polar front jet or mid-latitude eddy-driven jet, which, as its name suggests, is largely eddy-driven. So there is a bit of a difference in the sort of zonal mean situation in the southern hemisphere compared to the northern hemisphere, and that's because during winter, there's a distinct double jet structure. So at about 30 degrees south, there's the subtropical jet, which exists between about 100 and 400 hectopascal, and further poleward, there's a distinct separate jet, the mid-latitude jet. And so we see in this regional perspective, this clear split jet structure over the South Pacific Basin. And so that's quite different to what happens in the northern hemisphere during winter, where there's really only one merged jet structure. And this is sort of a combination of eddy and thermal driving processes. So as I mentioned, the subtropical jet has an important role for these tropical to extratropical interactions because it strongly influences both the Rossby wave source initiation as well as the dispersion of Rossby waves. And so we can get sort of an idea of what this looks like by looking at the total stationary Rossby wave number. And so this relates the meridional absolute vorticity gradient to the zonal winds. So what we see by looking at this plot of the meridional absolute vorticity gradient beta star is that there is this maximum in beta star, which coincides with the core of the subtropical jet. So where we have the subtropical jet, we tend to get Rossby wave generation. And this pattern of KS also helps to illustrate where Rossby waves can and cannot propagate. So these local maxima in KS along the westerly jets are preferred waveguides for stationary Rossby wave propagation. And then there's also regions where Rossby waves are unable to propagate. So that's in the tropics, where there are the upper tropospheric mean easterlies. And there's also this isolated region on the poleward flank of the subtropical jet, where that meridional gradient of absolute vorticity becomes negative. And so this should act as a barrier for Rossby wave propagation. And that's an important part that I'll discuss in the first part of this talk. So in this talk, I will be discussing the mechanisms involved in the establishment of the teleconnection from the tropical Indian Ocean in the first part. And then in the second part of this talk, I'll discuss the cause of the asymmetry between Western and Eastern Pacific heating anomalies, like what we see during El Nino and La Nina. So looking first at understanding the mechanisms of Indian Ocean teleconnections into the Southern Hemisphere during winter. And I'll motivate this work by just sort of discussing a couple of the impacts of the IOD teleconnection on Southern Hemisphere weather and climate. And so one of these important ones we saw with the record negative IOD event that occurred in spring 2016, which is shown with these SST anomalies, where we have these warm SSTs and increased convection in the Eastern Indian Ocean and suppressed and cool sea surface temperatures in the Western Indian Ocean. And so several studies, both here at NCAR and in Australia, indicated that this record negative IOD event contributed to the record low Antarctic sea ice extent that occurred in that same season. And that was because this increased convection that occurred in the Eastern Indian Ocean triggered a poleward and eastward propagating wave train towards Antarctica, where it then modified the local circulation there and contributed to this sea ice decline. In terms of Australia, looking at the impact of the IOD there, we saw in 2019, sort of in spring and towards early summer, the impact of a record positive IOD event. And so this is the opposite of before. So instead we have the increased convection in the Western Indian Ocean. And this contributed to large rainfall declines across much of Australia. And usually we see this impact in sort of southeastern Australia, but it was quite widespread in this time. And then this drying associated with the positive IOD contributed to the occurrence of these bushfires that occurred in 2019 and 2020. And this is something that we tend to see major summer bushfires tend to occur following a positive IOD event. But I will also note that although we had this positive IOD, there were also other things happening. For example, there was a Central Pacific El Nino event, which also promotes drying across Australia in this season, as well as a rare Antarctic stratospheric warming. So now getting into what this IOD teleconnection looks like sort of more generally, here I'm showing the teleconnection, so this is the dipole mode index, so an indicator of the IOD, regressed against various fields to show the initiation and propagation of this wave train. And so what we see, this is showing the negative IOD sort of teleconnection, so we see this increased convection, these negative OLR anomalies over the eastern Indian Ocean, shown by the shading. And this leads to strong divergent outflow, shown by these vectors, towards the southern hemisphere extratropics, where then when it encounters this subtropical westerly jet, it promotes the establishment of a Rossby wave source, which is shown here by this solid magenta contour. And as a result, this then triggers a poleward and eastward propagating wave train, similar to that sort of schematic that I showed at the beginning. However, during winter, as I also explained in the beginning, there is this region on the poleward flank of the subtropical jet where the meridional gradient of absolute vorticity becomes negative. And so when a poleward propagating wave train, like from the Indian Ocean, encounters this region, it should be reflected away from it, back towards the tropics and back towards the subtropical jet waveguide. But that doesn't appear to be the case. What we see in the observations, we see this apparent continuous Rossby wave train from the Indian Ocean into the southern hemisphere extratropics. And so this sort of disconnect between sort of what linear Rossby wave theory predicts and what we actually see in the observations motivated us to sort of understand how do stationary Rossby waves forced by the IOD propagate into the southern hemisphere across this barrier that's provided by the subtropical jet. And so studies haven't shown how a stationary Rossby wave can overcome this barrier provided by this negative beta star region. There has been some work looking at how Rossby waves can overcome this barrier in the tropics. And so that's by looking at including the mean meridional wind. And so studies have indicated that cross-equatorial propagation is possible because the mean meridional wind acts like a one-way tunnel from the north or the southern hemisphere or vice versa. But we were interested in looking at how this propagation across this negative beta star region occurs. So in order to understand the mechanisms involved in the establishment of this teleconnection, we've conducted large ensemble diabatic heating experiments with CAM5. So this is where we simulate the daily evolution of the Rossby wave response to a sudden switch on of additional diabatic heating in the eastern Indian Ocean. So that's shown here in the figure on the right. So in this framework, I generated a large ensemble of paired runs that with and without this additional heating and initialized these using random austral winter start dates. So these I took 90, 1st June, 1st July, and 1st August restart files. And so we're specifically focusing on the austral winter months because this is when we have the wintertime subtropical jet, which, as I've discussed, sort of acts as a waveguide and also promotes this effective Rossby wave source. So because I'm interested in the daily evolution, I integrated each of these experiments for 30 days because we know that the sort of extratropical response takes about 2 weeks to be established. And by looking at the ensemble mean difference between these paired experiments with and without the heating, we can isolate the forced response to this heating. So now looking at what this response looks like, so this is showing geopotential height anomalies in the upper troposphere as the shading, as well as wave activity flux anomalies, which are the vectors. And so this is the difference between the experiment and control simulations. And so here I show the evolution across days 3 to 11, looking at every other day. and then take the mean over the final 2 weeks of the integration to sort of get some comparison with the time mean in the observations. So looking here at the beginning of this integration, from when the steady heating is switched on, we start to see the establishment of the tropical response. So along the equator, in the first week, we start to see the development of this equatorial Kelvin wave, which propagates eastward away from the imposed heating anomaly. And then in this first week, we also see the establishment of the subtropical response. So we see this chain of high, low, high anomalies propagating eastward along the subtropics. Oh, and I should note here that this thick magenta contour shows that region on the poleward flank of the subtropical jet where beta star becomes negative. So it shows that barrier to stationary Rossby wave propagation. So because of this barrier, we largely see these anomalies being confined to the subtropical jet waveguide. So we get this rapid response by day 7, where these anomalies reach the central Pacific Ocean. And by the second week of the integration, we start to see the development of the extratropical part of the wave train, where these anomalies, these tails of the anomalies appear on the poleward flank of this negative beta star region. And by the mean over their final 2 weeks, shown in the bottom panel, it well resembles the observed Indian Ocean dipole teleconnection. And so because we have this good sort of coherence between the model simulation and the time mean in the observations, it enables us to sort of look at the mechanisms involved in its establishment. So we've identified 3 possible mechanisms for this wave train to overcome this apparent barrier and propagate into the southern hemisphere extratropics. So the first pathway, so the main pathway that we've identified, is the possibility that this wave train can burrow underneath this barrier in the mid-troposphere. So I've just copied this zonal mean plot of zonal wind in the southern hemisphere to remind that the subtropical jet is largely confined to the upper troposphere, and so is this region of negative beta star. So from about sort of 350 to 400 hectopascals, Rossby waves should be able to freely propagate into the southern hemisphere extratropics. And that's indeed what we see by looking at the same figure as before, but instead looking at the 550 hectopascal level. So we see this evidence of direct propagation from the eastern Indian Ocean towards the southern hemisphere extratropics, where we're below this barrier to Rossby wave propagation. In contrast to what we saw in the previous plot, we don't sort of get this rapid response along the subtropics since we are below the level of the subtropical jet's core. And this pathway is nicely illustrated, I think, by looking at this figure, which sort of shows a cross-section that traces the centres of these main 3 anomalies to the west of Australia, to the south, and then closer to Antarctica. So in these panel latitude height cross-sections, I've averaged the geopotential height over each of these regions and then shown them for each domain. So this subtropical anomaly I show from 20 to 40 south and so on. And so what we see here, by looking at the evolution, just for the 13 days here, is that the development of this anticyclonic anomaly in the subtropics largely occurs in the upper troposphere at levels sort of above or sort of in line with this negative beta star region, shown again by the magenta contours. And it's strongly baroclinic, so we have different signed anomalies at the surface. Whereas when we look on the poleward flank of this region of negative beta star, the centres of these anomalies are shifted towards lower levels in the atmosphere, indicating that this wave train is able to propagate freely and largely below this region of negative beta star. And we suggest that, so we have this clear difference in the structure from the sort of subtropics, where it's equivalent, where it's baroclinic, to the extratropics, where this response is equivalent barotropic. And we suggest that the development of this equivalent barotropic structure could be facilitated by strong vertical motion in the presence of the subtropical jet. So we have upward motion in sort of the vicinity of this cyclonic anomaly, which promotes the development of this equivalent barotropic structure. So the second pathway that we've identified is also the direct propagation across this barrier. So linear Rossby wave theory predicts that when a wave encounters this region on the poleward flank of the subtropical jet, it should be reflected to the tropics. And we do sort of see that in the first week of the integration, where this response is largely confined to the subtropics. But we also do see evidence of direct propagation across this barrier, where these wave activity flux anomalies seemingly just able to propagate across this region. And we see this both in the model, the simulations, as well as in the observed teleconnection. And so we suggest that this is because this region is meridionally narrow, and so we don't necessarily expect it to sort of act as a concrete barrier to wave propagation, so it's probably not sort of completely impermeable. And because it is only narrow, it also possibly violates the assumption of the WKB approximation, that the scale of this mean state varies less than the scale of these waves. And the final mechanism that we've also shown here is also the possibility that the wave can propagate around this barrier. So this region sort of only really exists in the Eastern Indian Ocean into the Pacific Ocean. And so from the Western Indian Ocean, waves should be able to propagate freely into the Southern Hemisphere extratropics. And that's what we see by looking at a similar experiment where we impose a heating anomaly at 60 degrees east, so further westward in the Indian Ocean. And we see evidence of direct sort of propagation from the Western Indian Ocean into the extratropics, where it would then sort of combine with the Eastern Indian Ocean wave train. So to summarize this first part of the talk, we've shown that the development of the Eastern Indian Ocean wave train follows a two-stage process. So we have this initial rapid propagation along the subtropical jet waveguide, and this is then later replaced by a poleward arcing wave train that resembles the observed Indian Ocean dipole teleconnection. We identified three possible mechanisms involved in the establishment of this teleconnection. So this first sort of this burrowing mechanism, and so this is the first time that this mechanism has been shown, where we have this direct propagation below this barrier, where beta star, the meridional gradient of absolute vorticity, becomes negative. And then we also find evidence of direct propagation across and around this barrier from the Western Indian Ocean. I haven't shown it here, but we also explored the role that transient eddy feedbacks play in establishing this teleconnection by contrasting these results with similar experiments conducted using a linear model. And we find that these sort of feedbacks, these nonlinear feedbacks, aren't required to establish this teleconnection. So we get a similar teleconnection pattern in the comprehensive GCM and in the linear model. So with future work, it would be interesting to isolate the key pathway to see which one of these three pathways is sort of the most important, and also to explore teleconnections into the Northern Hemisphere. So I've shown this plot here showing the total stationary Rossby wave number during winter in the Northern Hemisphere. And what we can see where there are these black shading, this indicates regions where beta star is negative. So we have this large region in the sort of North Pacific where stationary Rossby wave propagation should be prohibited. So it'd be interesting to explore how teleconnections can work across this barrier. So now I'll get into the second part of this talk, And so this is shifting focus from the Indian Ocean to the Pacific Ocean and understanding ENSO teleconnections and the asymmetry in these. So once again, I'll motivate this by discussing some of the impacts, this time focusing on Australia. And so we've really seen over the last couple of years the impacts of this current prolonged triple dip La Nina event, which is sort of very different to what you've been sort of experiencing here, where for the last couple of years there's been sort of highest on record, or at least very much above average rainfall for large parts of eastern Australia. And in particular this year, in 2022, as of early October, Sydney, so located sort of on the east coast in New South Wales, had already exceeded the previous highest rainfall threshold from 1950. And this was before the current La Nina event had really even peaked. So we tend to see these strong flooding events during La Nina years across eastern Australia. But I will also note, as before, that while we do have this sort of prolonged La Nina, there are also other phases, other climate modes that have spent sort of considerable time in their sort of rain-producing phases for eastern Australia. So the negative IOD over the last couple of years, as well as the positive southern annular mode. So we tend to see this asymmetry in the impact of El Nino and La Nina on eastern Australian rainfall. So I've shown here a scatter diagram showing the Nino 3.4 index on the x-axis and rainfall average across eastern Australia. That's in this white box here on the y-axis. And what we can see is that there's a stronger relationship between La Nina and eastern Australian rainfall than there is between El Nino and eastern Australian rainfall. So we don't tend to see, the magnitude of El Nino doesn't necessarily sort of tell us much about what we can expect in terms of a rainfall response. And this asymmetry can be partly linked to the asymmetry that we see between El Nino and La Nina events in the tropics. So this is looking at composites of El Nino and La Nina years during austral winter again. So this is years when each sort of part exceeds plus or minus 1 standard deviation of the Nino 3.4 index, showing La Nina on the top and El Nino on the bottom. So what we see in terms of the precipitation response is we see this increased rainfall across sort of the central and eastern Pacific Ocean during El Nino events, whereas during La Nina events, this rainfall anomaly is shifted westward, closer to the maritime continent. And associated with this westward shift of the rainfall anomalies during La Nina, we also see a different teleconnection pattern between these phases. So this is showing geopotential height in the upper troposphere. What we see is that El Nino is sort of associated with this typical sort of poleward arcing wave train pattern towards the southern hemisphere extratropics, whereas the pattern associated with La Nina has sort of less coherence with what's happening in the tropics, and instead we have these sort of more zonally elongated anomalies across the South Pacific Basin. So studies have indicated that this westward shift is linked to this westward shift of the convective anomalies. So for example, we see this PSA pattern is shifted closer to New Zealand and Australia compared to the equivalent low anomaly during El Nino. And a recent study also suggested that this asymmetry could be related to changes in the subtropical jet that we get in El Nino compared to La Nina. So when during El Nino, the core of the subtropical jet shifts eastward and is stronger, and then this also then should shift the wave train eastward. But it doesn't sort of fully explain this asymmetry and this more zonal elongation that we get during La Nina events. So here we want to understand the cause of this asymmetry between eastward and westward located ENSO events. And to do this, we've used the same experimental setup that we used for the Indian Ocean experiments, but this time imposed a heating anomaly in the sort of western Pacific Ocean at 170 degrees east, and an anomaly further eastward at 210 degrees east. So these are sort of idealized sort of locations, but overall they're sort of designed to mimic the locations that we get during westward and eastward located ENSO events. So like westward events like La Nina and Central Pacific El Nino, and eastward events like sort of canonical Eastern Pacific El Nino events. So this is showing a similar figure to what I showed earlier. So this is the geopotential height anomalies in the upper troposphere, so the difference between the experiment and control for the westward located patch on the left and the eastward located patch on the right. And again, looking at this daily evolution. So what we can see, focusing on this 170 degree east patch first, is we see a similar evolution, at least initially, to the Eastern Indian Ocean experiment. So we see the establishment of the Kelvin wave in the tropics, and then we start to see the development of the subtropical component of this wave train. So we get this strong, rapid response along the subtropical jet waveguide. And we end up with a response that propagates quite zonally and ends up with quite circumglobal propagation, so reaching into the Indian Ocean as well. And then eventually, when we look at the time mean over the final 2 weeks of the experiment, this ends up well resembling this observed La Nina teleconnection, apart from the change of the signs. So here I've imposed a positive heating anomaly in the Western Indian Ocean, but sort of the response in the South Pacific matches pretty well, just with the sign reversed. While in the 210 east experiment, so the heating patch located more sort of closer to the central Pacific Ocean, here we see a sort of a different evolution of the response. Instead, we get larger meridional propagation. So the response sort of reaches the South Pacific sort of faster than the western patch, and we get a more poleward arcing wave train. And so the centres of these anomalies don't really sort of evolve too much throughout sort of the course of the simulation, and they well match in the time mean response. And so there seems to be less zonal, sort of circumglobal propagation in this experiment, and so it largely ends up being sort of more regionally confined to the Pacific Basin. So we find that this sort of asymmetry, part of this asymmetry, can be understood from linear Rossby wave theory. So when we impose heating closer to the core of the subtropical jet, we get more zonal propagation. And that was also the case for the Eastern Indian Ocean experiment. But when we put this heating anomaly further eastward, away from the core of the subtropical jet, we're sort of less influenced by this barrier to Rossby wave propagation, and the wave is able to freely escape into the southern hemisphere extratropics. And we also see this sort of larger response, at least initially, in this western heating patch, again, because of the proximity to the subtropical jet, which promotes this larger Rossby wave source anomaly, which we can see with these solid contours, comparing the 170 degree east experiment with the 210 degrees east experiment. So it is clearly larger for the western heating patch. So while we can sort of understand these behaviours sort of from what Rossby wave theory sort of tells us, and it appears that in this eastern heating patch, it evolves in a manner that we would expect from sort of Hoskins and Caroli wave theory, where we get this eastward and poleward propagating wave train. But in this western heating case, the development of this sort of zonally elongated dipole in the southern South Pacific is sort of not really able to be explained from linear theory. And so we find that suggests that an additional mechanism is required to explain the development of this response. And we suggest that this additional mechanism is in the form of a transient eddy feedback that acts in the extratropical storm track. So here, just for reference, I've shown the climatological storm track in the southern hemisphere during winter. So this is calculated as the root mean square amplitude of high-pass filtered heights at 250 hectopascal. And what we can see is that there is this strong region of enhanced transient eddy activity across the southern Indian Ocean, as well as in the South Atlantic Ocean. But there's sort of less indication of sort of enhanced transient eddy activity associated with the subtropical jet, sort of along 30 degrees south in the southern hemisphere. So here we calculated the geopotential height tendency, shown with this equation, due to the horizontal convergence of eddy vorticity flux. So the way this sort of works is that this tropically forced wave from the Pacific Ocean interacts with this extratropical storm track and causes a rearrangement of the transient eddies in this storm track. And so this can then induce positive feedback, which can then either amplify these existing anomalies or even act to sort of modify their structure. And that seems to be what's happening in this Western heating experiment. So I show here the evolution of this height tendency in both the experiments, focusing on, so I average these over 5-day periods, so days 6 to 10, 11 to 15, and then I average over the final 2 weeks of the experiment. And what we see is that in both cases, even 10 days into this integration, these height tendency anomalies are weak, so both in these top panels, are weak and are not well organised. So this indicates that this initial response that we see is largely sort of just the direct response to this imposed heating. And it's not really until after about 10 days that we start to see the effect of these transient eddy feedbacks. And so in this 170 degree east experiment, by sort of days 11 to 15, we start to see the organisation of this sort of dipole in the South Pacific. So there's this cyclonic height tendency across sort of about the, sort of the subtropical South Pacific, and then these stronger anticyclonic height tendency across the polar cap. And by the final 2 weeks of the integration, this height tendency has sort of organised itself in a way that well resembles the height anomalies in this experiment over the South Pacific basin. So we find that there's a primary role of this feedback for modifying the Rossby wave response and promoting the establishment of this zonally elongated meridional dipole in the South Pacific basin. And so this is in contrast to the Eastern Pacific experiment, where we sort of largely just see that this setup acts to sort of amplify the existing height anomalies. So we find this difference between these two height tendencies in both of the experiments is quite subtle, but we find that this cyclonic tendency is shifted eastward towards South America, where it acts to amplify this cyclonic anomaly in the South Pacific. And as I mentioned before, with sort of these linear model experiments, we verified the important role that this feedback plays in promoting this asymmetry between Western and Eastern located heating anomalies by conducting similar experiments in a simple linearized model. So here we impose heating again in the same longitudes as we did with CAM5 and explore the evolution of the response for 20 days. And what we find is that there's sort of quite remarkably similar responses in both of these experiments. And so they evolve in quite sort of similar ways. And so what we see, for example, is this response is much more rapid in this linear model. Even by day 3, this Kelvin wave has reached South America, and we see this chain of high-low anomalies along the subtropics. And then we see thereafter, they each have this sort of poleward arcing wave train that is quite similar amongst the two experiments. So there are some subtle differences. For example, in this western heating patch, we see sort of that these anomalies are perhaps more sort of flattened compared to the eastern experiment, where they are sort of slightly more arcing. But overall, sort of the general appearance of these anomalies is similar between these two experiments, suggesting that this linear model cannot obtain a realistic structure and this asymmetry between western and eastern located heating due to the exclusion of this transient eddy feedback, like what we see in the observations and in the CAM5 simulations. So just to conclude this final part of my talk, so we show that the subtropical jet strongly influences the height response to Western Pacific heating. So this causes this prominent zonal and circumglobal propagation. Whereas for heating in the Eastern Pacific, these anomalies have more meridional propagation because they're further away from the subtropical jet core, and they just sort of disperse in this sort of classical Hoskins and Crowley manner. We find that this transient eddy feedback, which occurs after about 10 days in our simulations, appears to play a primary role in developing this time mean response. And that was confirmed with those linear model experiments. And that's in contrast to this Eastern Pacific heating, so reminiscent of El Nino, where it just seems to establish these already existing height anomalies. So I'll just give a very brief sort of summary of this talk and this work by sort of simulating the daily evolution of these responses to this sudden switch on of heating in the tropical Indian and Pacific Oceans. We've been able to really sort of elucidate the precise mechanisms that are involved in their establishment. And so this sort of information can't be gained from sort of the traditional approach of looking at sort of the time mean teleconnection. We identified those 3 mechanisms involved in the establishment of the Indian Ocean dipole teleconnection in the first part, and then linked this asymmetry in the response to El Nino and La Nina in the second part to the differing roles of a transient eddy feedback. And so these results have sort of relevance for improving seasonal prediction, particularly over Australia, where we're impacted by both the Indian Ocean dipole and ENSO, because it demonstrates that a good simulation of these teleconnections is reliant on having a good simulation of the subtropical and mid-latitude jets, and particularly getting that separation between the two jets over the South Pacific, which is sort of, models are sort of starting to improve on, but that is something that's sort of quite, has been notoriously challenging to simulate. And with that, I'll finish there. Thank you so much.
Thanks for the great talk, Jerry.
Yeah, it was what?
Oh yeah, I think we don't need to use them. Yeah.
Okay, so yeah, that was great. Just at the second half there, bringing it back to Australian rainfall, you noted that during La Nina events, there was almost always flooding in eastern Australia, but El Nino events, the signal for drying wasn't as strong. So how do you relate that Australian rainfall signal back to this asymmetry in that you're looking at the extratropical response?
Yeah, so it's sort of, I guess, the response that we see during El Nino is shifted sort of further eastward, so it is sort of more away from Australia, so we're not sort of getting a direct influence. But I think that's definitely an outstanding question. So here, and just showing you just the seasonal mean teleconnection. And I think what is sort of really lacking in our understanding of how ENSO impacts Australian rainfall is sort of how ENSO impacts weather systems, and which then actually produce rain or prevent rain from occurring. So I think that's sort of something that I'm currently sort of trying to understand. And we do sort of see that La Nina is associated with this increased blocking anomaly in the South Pacific, in the Tasman Sea. And so that, promotes cyclogenesis over eastern Australia. But yeah, in terms of why some El Nino events lead to severe drought, like 1997, but then others don't, that's sort of something, still trying to understand.
Thanks.
Were we going to get the Slido up for any online questions? No. Yeah, but you don't need the mic. I think they're in the room.
So you chose to do this Eastern Pacific heating in the center of the ocean and not sort of be like a canonical, and so where the heating would be further east.
Yeah.
So why did you choose that?
Yeah, so that's because since we're imposing direct sort of atmospheric heating, so we're imposing a diabatic heating anomaly. And so during El Nino, canonical El Nino, you'll have, I have a lot of SSTs, but so the sea surface temperature anomaly is sort of more Eastern Pacific, but the associated maximum convective anomaly occurs more sort of in the central Pacific Ocean. So like we're showing here, this maximum rainfall response is sort of westward of the SST response during El Nino.
So does a canonical ENSO have less effect on Australian precipitation than a Central Pacific?
I'm not too sure about that. I think that could perhaps be sort of the key maybe to explaining why some El Nino events don't have an impact, whether there is some difference between canonical, Central Pacific, Modoku sort of El Nino events. Yeah, that could perhaps be the difference there,
This is a very interesting experimental design. I'm used to seeing sort of these diabatic heating bubbles being in sort of dry GCMs and looking at your like your Kelvin wave response and stuff like that. And I'm sure people do these in moist GCMs. I'm not familiar with the literature. But I'm having done like big moist bubble experiments with CAM5 with all its moist physics turned on. These big bubbles end up sort of like breaking up into like 60x resolved updrafts. And so I'm a little concerned that the response of CAM5, CAM6 moist physics to these big diabatic heating bubbles might be a little unphysical. And I wonder if maybe a more natural way to make the model respond to that is instead prescribe a surface heating bubble. So it's heating from below, and that way you can activate your deep convection schemes because you're moistening the boundary layer, and it just seems like maybe a more natural way to mimic how the atmosphere would anomalously heat.
Yeah, so we decided to do this sort of direct heating because it sort of allows you to have sort of better control of where the sort of, deep convection response occurs. But yeah, that is something that definitely we sort of thought about, because we find that when we do impose this heating in CAM5, we not only have this imposed heating, but then CAM also has its induced heating in response to this heating. Yeah. So we do end up with quite a pretty large anomaly. Yeah. To sort of be sort of double sort of what we impose. And so then as we get further into the integration, it's sort of hard to sort of see, is this response because of the imposed heating or is it because of the induced heating? But I did sort of do a couple of tests looking at sort of SST anomaly experiments and comparing them, and it actually found that it was actually like a pretty similar response. But sort of, in sort of the diabatic heating response as well as sort of the teleconnection. So perhaps, there's maybe not too much sort of more control that we're necessarily
I'm not surprised. I didn't think it was going to impact your conclusions, but I just wanted to express my thoughts about the bubbles.
Yeah, no, I agree. It's, definitely, there's a lot of heating that it does produce in response, which, is sort of a bit of an issue, but we sort of see, so we do see this similar response in the linear model in some cases, that sort of maybe gives us a little bit of confidence, but it's definitely something to consider when interpreting the results.
It was just excellent. I just feel like you provide so much insight into, things are delicate and complicated. And
yes.
It's not one, set of mechanisms doesn't always work for different regions.
That's right.
So it made me think about in our coupled model, your approach would be really helpful for, you could put in the mean state of the coupled model and then impose your diabatic heating, a little like what Ruyun Chen did for the northern teleconnections, and see what aspects of the mean state in the coupled model are responsible for deficiencies in the teleconnections, because I'm sure they're there.
Yes.
And I just think that's the way forward to really, really getting at the model deficiencies in these teleconnections.
Yeah.
Yeah.
Yeah, that's sort of what, with my postdoc work, I'm sort of now looking at more sort of pacemaker style setups.
Yeah.
So, yeah,
Well,
imposing
that's
the
what
model
I
from-
had in mind,
Yeah.
exactly. And
Yeah.
I remember there was someone some years ago, I forget who it was, someone maybe in Julie's group, who was going to take our tropical Pacific pacemaker runs and look at the
Oh,
southern
Dawn
hemisphere.
and Dawn, I think.
Yeah.
People just say, yeah.
And they were just so poorly represented, I think, that that person didn't pursue it. But at least now you
Yeah.
can understand
Yeah.
why they might be poorly represented. So it's just a really great.
Yeah, I'll be doing those experiments using the Australian model Access CM2. I think
Okay.
that's sort of quite an issue because it has a sort of biannual ENSO
Yeah.
as well, which is sort of,
Yeah, I
interesting
mean,
stuff.
even apart from deficiencies in ENSO, if you
Yeah.
gave it these idealized diabatic heating anomalies, just taking the mean state of
Yeah.
the model, how it might respond differently.
Yeah, it'll be
Yeah.
interesting to see how that goes.
Hi, Zoe.
Hi.
Okay, I'm very interested in your research and I think it's very inspiring. And in your presentation, you emphasize the important role of the eddy to make the teleconnection to transport to more northward. So my question is about, I don't know my understanding is right or wrong. So it's the eddy that transports the velocity anomalies caused by the convection in the tropics to the more poleward, and then it will have the connections in the more higher latitude, right? What I understand is right or wrong.
Yeah, so sort of the zonal.
It's the eddy transports the vorticity anomalies to northward. Oh yeah, this.
Yeah, from sort of the extratropical storm track, yeah. So so we have this sort of, so we have this poleward propagating wave train.
Yeah.
And then we also have these synoptic eddies that are sort of excited in the extratropical storm track. And so it's this interaction, sort of eddy mean flow interaction.
Yeah.
That sort of promotes this different structure of this response.
The vorticity anomalies is caused by the convection, right? In the tropics region, tropical region.
I guess there would be some, sort of excitation of those anomalies, but then these in the extratropical storm track, these anomalies are just sort of internally generated as well. But there is sort of links between ENSO and like the southern annular mode, so the storm track. The ENSO can sort of excite this sort of shift in the sort of eddy-driven jet as well.
Okay, and this is a model simulation. And in the model simulation, do you have the experiments that shut down the eddy influence or keeps the eddy influence, and you compare them?
No, so that's definitely something that could be sort of a nice extension to sort
And
of.
in your experiments, how do you keep the eddy influence, but how can you compare that the experiment without eddy influence?
So that's really just sort of by comparing this CAM5 experiment, which includes this feedback, to the linear model, which doesn't have this interaction, this transient eddy feedback.
Compared to the linear.
Yeah, so in CAM5, I don't sort of have the ability
In the linear
as
model,
well.
you don't have the eddy influence.
This transient eddy feedback is absent in that model.
Okay, I understand. Thank you very much.
No worries.
I also had a question about the eddy feedback. I was wondering, and it's here kind of in the lower panels here, the western heating gives you kind of more warming overall in the tropics. So are you kind of invoking the wave inducing those eddy mean flow feedbacks, or do you think there's kind of a role for that overall warmer tropics in like here
Yeah.
compared to this one, which has less warming overall and kind of driving that eddy feedback?
Yeah, so we more sort of link it to this sort of circumglobal propagation of this stationary wave and this sort of perturbation of the sort of synoptic eddies in sort of hemispherically, really. Because I think, so there's this interaction between sort of ENSO and the southern hemisphere extratropics, both with these sort of poleward propagating wave trains, which then sort of interacts with the southern annular mode and the storm track. But then there's also that sort of more zonally symmetric mechanism with SAM and ENSO, that interaction. But I think that mechanism is more sort of confined to the summer, austral summer season. So we sort of suggest that this is sort of the main feedback in the winter season.
Okay. Any other questions? Any online? Did you have another one?
I'm so intrigued by that, the mean state of the storm track. I feel like if southeastern Australia and New Zealand weren't there, there'd be so much less asymmetry between the Indian Ocean sector and the Pacific Ocean sector.
Yeah. Yeah, I sort of haven't sort of looked at any sort of experiments removing those. Yeah, I don't sort of know how much. I think that was something we wanted to do, sort of see well, what role does Australia actually play in New Zealand, but yeah, I don't think it's sort of really been shown.
Exactly, I think that would be a really nice thing to pursue, just chopping off that southeastern part of Australia and New Zealand. I think it's the whole structure in the SPCZ that is anchored by that. But in that,
How that landmass interacts,
fundamental to where that subtropical jet barrier is,
Yeah,
which
it doesn't
then
seem like it's
controls
just a,
all of your.
Yeah, it's not just a coincidence. Yeah,
Exactly.
It's related to it. Yeah.
Yeah.
I just thought it was more just because you've got the warm pool and that's climatologically driving a kind of climatological stationary wave. I feel like Hoskins and Caroli kind of argued that that's why you have this structure.
There's the split jet structure. Yeah.
Well, let's see. I feel like it hasn't been actually, right, I think it's hypothesized.
Yeah.
Yeah.
Well, yeah, I can't remember how they showed it, whether it was just with the linear model and putting in that diabatic heating and then they kind of get the overall structure.
Okay.
But yeah, I agree. I always felt like the topography of New Zealand was important.
Yeah, I agree.
Any more? I guess I had one more, which is, have you thought about climate change and the strengthening of the subtropical jet and how that might affect your teleconnections in the first part?
Not really too much. I sort of just mainly been focusing on sort of these sort of present day scenarios. But yeah, I think so. I mean, would sort of be expecting, I think, sort of maybe an eastward sort of displacement of these Pacific Ocean teleconnections, and perhaps also changes in these transient eddy feedbacks. But yeah, I'm not too sort of sure what role, sort of how that sort of interacts with the Indian Ocean dipole, sort of how I think it's like positive IOD events are becoming more frequent. Yeah, how that sort of might affect the subtropical jet and that sort of wave connection. Sort of very interesting. But yeah, I haven't sort of looked into future climate scenarios.
Well, if there aren't any online, I guess not. Okay, well, thanks for the excellent talk.
Thank you.
Just remember that, Zoe's here for 2 weeks, so if you want to talk more, she's around.
First time in the summer.